Let's check the first question here. A sphere of radius 2.1 millimeter falls with terminal constant velocity through a liquid as shown in the picture, in the figure. Okay, so the first information which we get is radius 2.1 millimeter, which we need to convert to meters. So let's just do that here itself. Three forces act on the moving sphere. The weight of the sphere is 7.2 into 10 to the power negative 4 Newton. That's the weight. And the upthrust is 4.8 into 10 to the power negative 4 Newton. The viscous force acting on the sphere is given by the formula which we have here, Fv equal KRV. So it says that R is the radius of the sphere, V is the velocity, K is a constant, and the value of K is given to us, which is 17. The first question is asking, determine the SI base units of K. So what we will do is, first we will take the formula which is given to us for the viscous force, Fv equal to KRV. Then we are going to arrange it for K, because that's what we want to get the base units for. So we'll make K as a subject. So Fv equal R over Rv. Again, K equal Fv over Rv. So now we'll write the units for them. So I'm just going to change the color here. Fv is a force, so the unit will be Newton. R is radius, the unit is meter. And velocity is meter per second. So we can go ahead, write meter and meter will become meter square over second. That second we can take up, meter square stays down, and then we can write the final answer, Newton second m to the power of negative 2. So what we did is we just took this m square up just to make it into a standard format, and we got it as negative 2. Let's look at the next one. Use the value of the upthrust. So let's check what's the value of the upthrust. Yeah, here. So we'll write that the value of the upthrust is 4.8 into 10 to the power negative 4 Newton. I'm just writing you a little like a inverted square type, so that we don't get confused between U and V. Okay, so that's the value for 4.8 into 10 to the power negative 4 Newton. And it's asking us use the value of upthrust acting on the sphere to calculate the density of the liquid. So from the upthrust we want the density. So what do? So we need to recall that upthrust is actually the weight of the liquid displaced. Okay, so we can write that as the mass of the liquid displaced times g, because weight is mg. And the mass we can write as density times volume times g, because we know that density rho is mass over volume. So we can get the mass as density times volume. So that's what I have done here. I've substituted it. So that's our upthrust. Okay, or you may recall that this is a direct formula which we learn. So you can use this directly. In case if you don't remember, you can always derive it. What do we want? We want the density. So density is equal to, we'll arrange the formula from here. Density is equal to upthrust over volume times g. And now we need to substitute the numbers here. So let me just make a little space here. I'm just going to make it a little smaller, resize it. Okay. So now what we'll do is we are going to write upthrust over volume. It's a sphere. If you read in the beginning, it says it's a sphere. So 4 by 3 pi r cube. That's the volume of a sphere times g. Now we have to substitute the numbers. Upthrust is given to us 4.8 into 10 to the power negative 4 over 4 over 3 pi r cube. If you remember, r cube was 2.1 millimeter and we converted it into meters. 10 to the power negative 3 cube times 9.81. I'm taking it as 9.81 because that's the value which they have given in the beginning of our paper. You can also take it as 9.8. Anyways, when we calculate this, it comes out as 1262.6. Now we will use significant figures to reach to the final answer. So if you check this number 7.2 into 10 to the power negative 4, that's 2SF. This one is also 2SF. Okay, so our final answer can be 2 or 3SF. So I'm going to take it as 2SF. So if I round it off to 2SF, this will come out as 1300 kg per meter cube. The unit is given to us. So that's the second part. Let's check. Next, on the figure which is given to us, draw 3 arrows to show the direction of the weight. So what they are asking, the direction. Okay, direction of the weight, the upthrust and the viscous force, and label these arrows as W, U and FV respectively. So let's go back. This is our picture and we want to show the forces here. So I'm going to draw the weight, obviously downwards. The upthrust will be upwards, that's why it's upthrust. We are going to write it as U. And then FV, that was our viscous force or the drag force, that also will draw it upwards. So let me just make it a little smaller, even though it does not matter, but just to show the magnitude as well, I'm just making them a little bit smaller so that they are going to anyways eventually balance the weight. So this is our picture. They are asking for direction. Weight is going to act downwards, upthrust upwards, and the viscous force will also be upwards. Then it's asking, determine the magnitude of the terminal velocity of the sphere. So now we want to find the value for V. Now you need to first remember the equation or the equilibrium which it will reach to when it starts moving with the terminal velocity. So I'm just going to draw the free body diagram here. You have the weight acting downwards, FV is acting upwards, and our upthrust is also acting upwards. Okay, I'm just going to draw it a little bit bigger so it's on the same object. So when it reaches the terminal velocity, the weight should be equal to the upthrust plus the drag force. Okay. Now we need to find the velocity. Let me just try write V like this just to remember that it's the velocity. So what we are going to do is, okay, let's go back. So what we are going to do is we are going to first write FV as W minus U. This FV, if we remember what was the formula here, KRV. So let's just copy that here. KRV equal W minus U. We want V, so I'm just going to keep V here and remove K and R from there. So W minus U over KR. Now if you check, we have the value for W, value for U, K, R, everything is given to us. So we need to just substitute 7.2 10 to the power negative 4 minus 4.8 times 10 to the power negative 4. So that's from the given which is in the problem itself. And then K is also given to us, which is 17 times 2.1 times 10 to the power negative 3. That's the value for R. We can put that into calculator and that will come out as 6.7 times 10 to the power negative 3. And that's two significant figures, so I'll just copy it here. That's our answer. For velocity, the unit is given to us, so no problem, we don't have to write the unit again. Let's go to the next one. Now it's a question on projectile. We can straight away see that, and it's a horizontally projected object. What is the object here? It's a water. It's not an object, so kind of it's the water which is leaving the hose pipe with a horizontal velocity of 6.6 meter per second. The point P is at a height h. Water hits the ground at point Q. The horizontal distance between P and Q is 3.5 meter. Air resistance is negligible. Assume that the water between P and Q consists of non-interacting droplets of water, and the only force acting on each droplet is its weight. Now, they have given the answer here, kind of like they have given an indication that you have to focus on this point. If you read the first part, explain briefly why the horizontal component of the velocity of a droplet of water remains constant as it moves from P to Q. Obviously, there is no force acting in the horizontal direction because they have already told us the only force which is acting is the weight. So there is no horizontal force. No horizontal force. Okay, there is no horizontal force acting on the droplet. Okay, next, show that the time taken for the droplet of water to move from P to Q is 0.53 seconds. So time, now we can get time from the horizontal values as well as from the vertical values. So for the horizontal, if we check, we have got the range here, which is in the horizontal direction. Obviously, range is in the horizontal direction. We also have the horizontal component of the velocity, which remains constant throughout. So we can use range is equal to Vx, the horizontal velocity, times t. That is the time, yeah? So t is equal to range over Vx. What's the range? 3.5. Vx is 6.6. You can calculate that, and that's it. We showed it. 0.53 seconds. Now, as soon as you got the time, there is something which is which you need to register in your mind, that now we have got the time for vertical motion as well. And you can see the next question is asking calculate the height h, and we are going to use one of the kinematics equation. So I'm going to use this. Delta y is v y I t plus half at square. Now you can also write it as like I have written Vyi just to make it sure that this is the initial velocity which I am taking in the formula. That's what comes in the formula. Okay, don't worry about the different notations. Sometimes we write it as U. That's also fine. Okay, now Vyi. Think about it. Vyi. What is it? The initial vertical velocity. Initially, how did we project it? We projected it horizontally, correct? We projected it horizontally. So that means Vyi is 0. There was no initial vertical velocity. So this whole thing is going to become 0. Delta y is the h, height. Half acceleration due to gravity, I'm going to take it as 9.81. See that I'm not taking negative. Even though we know that acceleration is a vector quantity, we have to take care of the direction. But because we are calculating height, we don't have to write it as negative. Times t. Do we have the time? Yes, 0.53 square, which we calculated in the previous part. If you calculate this, this comes out as 1.38. Check the significant figure. All the numbers given values are 2SF. So our final answer also will keep it as 2SF. That's 1.4. Okay, let me check. I had, yeah, okay. Okay, so that's this C part. Let's check more to it. D. For the movement of a droplet from P to Q, state and explain whether the displacement of the droplet is less than, more than, or same as the distance along its path. So now they are trying to find out whether you know the difference between displacement and distance. So if you look at the droplet, that's the path of the water droplet. That means that's going to give us the distance. It is a curved path, and that's our distance. Displacement is the shortest distance between the final and the initial position, which will be this. This is our displacement. Obviously, displacement here is less than distance, which we can see in the picture, as well as we know that it has to be the shortest distance between P and Q. So our answer, how do we write our answer? So we can write displacement. Okay, let me change the color here. Displacement is the shortest distance, or the minimum distance, as you wish to say, is the shortest distance between P and Q. And just to, it's only for 1 mark, so that should be enough. But if you wish, you can go ahead and write distance. In this case, the path of the droplet is curved. Okay, therefore its distance will be more than the displacement. Okay, but there is no need for that. It's only 1 mark, so we can stop here. Calculate the magnitude of the displacement of a droplet that moves from P to Q. So now let's go back to the picture. So it's asking us now to calculate this displacement. What is this? That's what it's asking. Height, if you remember, we calculated that is 1.4. I'm going to take the unapproximated value, which was 1.38. We can see that this is a right angle triangle. So we can use Pythagoras theorem here. So let's do that. Displacement square is equal to 1.38 square plus 3.5 square. So PQ square is equal to 1.38 square plus 3.5 square. Don't forget to take the square root. So PQ will be equal to square root of 1.38 square plus 3.5 square. And we can get this answer as 3.76. Round it off to 2SF, 3.8. Let's check the next problem. Now here we have got a jet of water which is hitting vertical wall at right angles. There are some values given to us in the picture itself. The water hits the vertical wall with a velocity of 5 meters per second in horizontal direction. The cross-sectional area of the jet is provided. The density of the water is provided. The water runs down the wall after hitting it. Show that means it's not rebounding, it's running down the wall. So it's coming to rest kind of. So that's why it's running down the wall. Show that over a time of 1.6 seconds, the mass of the water hitting the wall is 1.2 kg. Now, normally, whenever this kind of problem comes, you need to know that water is traveling with some velocity, and that velocity is going to give us the idea about the length, how much distance or how much length it travels in a second. So if you look at the velocity, it's 5 meters per second. So it's giving you an idea that in 1 second, it's traveling 5 meters. That's the information which you have to get from the velocity. Okay, now why should we know that? So let's check. Here it's asking for the mass. Now mass, how do we get mass? How can we get mass here? We have been given the density. Density is mass over volume. So mass should be density into volume. Now we have to figure out what's the volume. Volume should be area of cross section times length. So now check. See, the length is not given to us, but instead they have given us the velocity. Okay, so what do? We can find the length traveled by the water in 1.6 seconds by multiplying the velocity with the time. Okay, distance is equal to speed multiplied by time. That's the formula which we are using. So 5 multiplied by time is 1.6. That gives us 8. So let's go back to the mass. Substitute the numbers. 1 into 10 to the power 3. That's the density. Okay. Area of cross section is 1.5 times 10 to the power negative 4 times length is 8. And we can use our calculator. Let me just quickly check with the calculator what answer do I get here. 0.5 times 8. That gives me 1.2. Yes, that's the answer, 1.2 kg, which is what they are saying. So that's done. Next, calculate the decrease in horizontal momentum of the mass of water due to hitting the wall. The decrease in horizontal momentum, that means we want to find the change, and change is always final minus initial. And as we discussed, as we were reading, we know that it's coming to rest, that's why it's running down the wall. So final momentum is obviously 0. Initial momentum we can find by multiplying mass with the initial velocity. So 0 minus what is the mass which we found, 1.2, times the velocity with which it was traveling is 5. So if we calculate that, that comes out as -6. Because it's talking about decrease, it's saying decrease, so we don't have to write negative, we just write 6, but don't write just 6, write it as 6.0, just because we want to follow the SF to SF. Magnitude of horizontal force exerted on the water by the wall. Force and momentum, they are connected by Newton's second law. That's rate of change of momentum, so we will write that. And momentum change we already calculated. The time is given to us. If you see, this is the time, 1.6. Why are we taking 1.6 seconds? Because we use the mass as 1.2, and you can see that it's connected. To find 1.2 kg we use this time, so that's the time which we are going to use, and obviously that's the time which is given to us. So 3.75, that's the answer. Round it off to 2SF, you get it as 3.8. Okay, so the final answer, you can see I'm writing it is in 2SF. That's just because all the numbers here which they have given to us, they are in 2SF. State and explain the magnitude of horizontal force exerted on the wall by the water. Now, on the wall, so on the water it was 3.8, so obviously on the wall will also be 3.8. Yeah, was it 3.8? Yes. So what's the reason? Obviously our well-known Newton's third law of motion. What it says, every action has an equal and opposite reaction. You can go ahead and write that, but it's only for 1 mark, so that should not be a problem. Okay, then next is pressure. Pressure is force over area. Force we got it as 3.8 over area of cross section is given to us in the problem, 1.5 into 10 to the power -4. Let's just check. Yes, and we can calculate that 25333.3. we want to put it in proper significant figures, so I'm going to move this decimal place 1 2 3 4 here, so that will become 2.53 times 10 to the power of 4, which we can write as 2.5 times 10 to the power of 4 to SF. So it's the scientific notation and proper significant figures. Okay, let's now do the next problem. A child moves down a long slide as shown in figure. The child moves from rest, so here he's moving from rest in the beginning. At the top end X of the slide, an average resistive force of 76 Newton opposes the motion of the child as they move to the lower end Y of the slide. The kinetic energy of the child at Y is 300 joules. So here KEY we can write as 300 joules, and we can write KEX as 0 here. There is some more information given. The decrease in gravitational potential energy of the child as it moves from X to Y is 3200 joules. So from here to here, as the child moves, the decrease in GPE is 3200 joules. Now, as soon as you look at it, you can see that if this was the decrease, we should have got an increase of 3200 joules in kinetic energy. That's not the case because we have got some resistive force on the slide. Now determine the ratio of kinetic energy of the child at y when the resistive force is 76 Newton and when there is no resistive force. So when the resistive force is 76 Newton, they have given to us, that's 300. When there is no resistive force, that means all of the GPE which decreased by 3200 joules, that should have been the increase in KEY. So it started from a zero kinetic energy, so it should have gone to 3200 if there was no resistive force. So that is 0.0937, which we can round it off to 2SF, 0.094. Okay, I hope that you get that point. If there was no resistive force on the slide, then whatever is the decrease in GPE should have been the increase in KE. And that's why we are writing the denominator as 3200 if there was no resistive force. Now, next part, it's asking for speed. The same question, but it's now asking for speed. So we need to know that the speed, so what's the relation between kinetic energy and speed? KE is half mv square. So KE is directly proportional to v square. So we can, because it's a ratio, the masses are same, so they will just cancel out. So we can write, because it's just speed, not speed square, so we need to have square root of KE. So how do we write it? KE when there is resistive force over KE when there is no resistive force. Now we don't have to actually write it down. Just for the sake of explanation, we already calculated it, that ratio we calculated, this value we actually calculated here. So we have to just put that number in the square root. You have to take the square root of it. That will come out as 0.3061. You can use calculator and check that. We will round it off to 2SF, 0.31. Okay, now we want to find the length of the slide from X to Y. So for that, we need to know what's the energy conversion taking place. So the GPE, gravitational potential energy, the change or the decrease in GPE is going to appear as the increase in kinetic energy, and some of the energy has to be used for doing the work done against the resistive force. So 3200 was the change in GPE, change in KE was 300, and that's equal to work done. So work done will be equal to 3200 minus 300, which is 2900. Work done is force times distance, which is equal to 2900. Force, we already know resistive force is given as 76, so the distance will be 2900 over 76, which will come out as 38.15, which we can round it off as 38. Okay, then it's not over yet. At the end of the slide, the child is brought to rest by a board, which we can see here, and there's a spring here attached. The spring connects to the board to a fixed point. The spring obeys Hooke's law, and the spring constant is given, which is 63 Newton per meter. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes 0, so the child comes to rest, and the elastic potential energy has increased to its maximum value, which is 140 joules. Calculate the maximum compression of the spring. So it's asking to calculate X or E, as you might have learned in your classes or in the textbook. It's giving us the elastic potential energy value, which is 140. Elastic potential energy formula is half kx square equal 140. So this is a straightforward problem. Half times k value is 63 times x square equal 140. Rearrange the equation, take the square root, and you will get the value for x as 2.108. Again, rounding it off, 2SF 2.1 is our answer. Then it's asking calculate the percentage efficiency of the transfer of kinetic energy of the child to the elastic potential energy of the spring. So if you remember, the child came in with an energy of 300 joules, which is from our previous part. Then that energy got converted to 140 joules of EPE. Remember, percentage efficiency of any kind is always output over input times 100. So here output, what, how much we got? 140. Input was 300 times 100, and that gives us 46.67, which we will round it off to 2SF. You'll get 47. Okay, next we want to plot a graph between EPE and X. It says that the compression is changing from X equal to 0 to X equal to X0 or X0, and that is actually the maximum compression. So to get the sketch, we need to know what is the equation which we are going to plot. So here we have got EPE is half kx square, so it's kind of quadratic equation. So it should be parabolic in nature, it should curve. We need to know that whether it's going to curve upwards or downwards. So what we can think of is what could be the gradient between EPE and X. So let's just look at one more formula which we should be knowing, which is half Fx, because Kx is F, so we can write as Fx. So we can see that the gradient can give us information about the force. And as we move from zero compression to maximum compression, the force should increase. That means it should be a curved line. Okay, it should be a curved line with increasing gradient. Okay, so that's how we can draw our graph. Next question. State the conditions required for forming a stationary wave. So for forming stationary wave, we require two waves which must have same frequency. What else? They should be traveling opposite to each other, or they should be traveling in opposite direction, and they must overlap. So we can write this like this: when two waves of same frequency traveling in opposite direction overlap, we get a stationary wave. Okay, now next is state the phase difference between any two vibrating particles in a stationary wave between two adjacent nodes. What does that mean? So let's draw a stationary wave. I'm just going to draw it a little colorful here. And we have got two nodes here. So this is one node, this is another node, actually three nodes here. What is it asking? Any two vibrating particles in a stationary wave between two adjacent nodes. That means between these 2 points, yeah? So between these 2 points, all the vibrating particles are going to achieve their maximum displacement, that is the amplitude, together at the same time. That means the phase difference is going to be 0. So that's a peculiar characteristic of the stationary wave, that all particles will, between adjacent nodes, will reach their amplitude, that is their maximum displacement, at the same time. Next, let's see what's the next question. It seems that it's a Doppler effect problem. A motorcycle is traveling at 13 meters per second along a straight road. Rider of the motorcycle sees a pedestrian standing in the road directly ahead and operates a horn to emit a warning sound. Pedestrian hears the warning sound from the horn at a frequency of 543. The speed of the sound in air is 334. So we want to find the frequency of the sound emitted by the horn. That means we want to find the frequency of the source. So let's recall the formula. Frequency of the observed observed frequency is equal to the source frequency V sound over V sound, that means sound velocity of the sound. In this case, it will be minus velocity of the source. Why minus? Because the motorcycle is traveling towards the pedestrian. So that means the frequency has to increase. That's how we can remember it. The frequency has to increase. Now, if the frequency has to increase, that means in the denominator, we should have a lower value. So that's why we have got a negative. If it was going away, that means the frequency should be less. That means the denominator should have been more. So in that case, we will put a plus sign. Instead of minus sign, we'll have it as a plus sign. But here, motorcycle is traveling towards the pedestrian. So the frequency observed by the pedestrian is going to be more, and therefore we have a negative in the denominator. Now we are interested in finding this because everything else is given to us. So we need to rearrange the equation, write it as V sound minus V source over V sound times FO. Let's write that with the numbers now. So that will be 334 minus 13 over 334 times 543. And if we calculate that, that comes out as 521.9. Rounding it off to 3SF this time, because we can see that all the given numbers are in 3SF. Check this. All given numbers are in three significant figures. So we can write that as 522. Next, motorcycle rider passes the stationary pedestrian and then moves directly away from her. As the rider moves away, he operates the horn for a second time. The pedestrian now hears the sound that is increasing in frequency. Oh, that's different from what you would usually experience, because if the motorcycle is moving away from you, the frequency should decrease, but here it is increasing, and that's what the question is asking. State the variation, if any, in the speed of the motorcycle when the rider operates the horn for the second time. So because the frequency is increasing, it is an indication that the speed of the motorcycle is not constant. This time the speed, as he moves away from the pedestrian, his speed is decreasing, and therefore you can see that there is an increase in the frequency observed by the pedestrian. Okay, so we'll write speed decreased. Okay, then next question is on, is it a continuation of this? Yes. The next question is on the polarized monochromatic light. So we pass a polarized monochromatic light through a polarizing filter, and the angle is given as 20. We want to find the ratio of the amplitude. So we should be knowing that amplitude is, or intensity is directly proportional to square of amplitude. That means if I want to find this ratio, it should be the square root of transmitted light intensity over the incident light intensity. And from Malice's law, we know that I transmitted is equal to I-O. Let me write this as, we normally write it as I-O. So, and that's what is written here. I-O cosine square theta. In this case, we'll write I-O cosine square 20. So we can substitute here I0 cosine square 20 over I0. These get cancelled out, and we will get this as cosine 20. The value for that is 0.939. We can round it off and write it as 0.94. Next, it's asking the filter is now rotated about the direction of the light beam. From its starting position, the direction of rotation is such that the angle of transmission axis to the vertical initially increases. Okay, so the angle is increasing. So we can see in the picture, this is our transmission axis, this is our vertical axis. So that means it's rotating. So this is a vertical axis, the angle is increasing, so they must be rotating this way. Calculate the minimum angle through which the filter must be rotated so that the intensity of the light returns to the value that it had when the filter was at its starting position. So that means when it was I0 cosine square 20, that's our initial position. It has to come back to the same position again, like means you have to get the same value again. So for that, we have to concentrate on the angle. So if you look at this formula, I0 is a constant value. This angle is what is changing. So we are continuously rotating it. So the angle is going to change. 20 will become 30, 40, 50, 60, and that's what is going to change the transmitted intensity. But we want to get it back to what it was in the beginning. That means we should have the same value of cosine. So cosine theta gives you the same value for cosine theta and cosine 180 minus theta. That means the theta and 180 minus theta gives you the same value for cosine. So that means cosine 20 and cosine 180 minus 20 is 160 should give us the same value for intensity. It's asking you by how much calculate the minimum angle through which the filter must be rotated so that it returns back. So you can see that this is our initial position. Okay, we want to find out what's the angle of rotation from this position. We know that this 160 is from the vertical axis. So this 160 degree is from the vertical axis. So in order to get it from the initial position, we have to do 160 minus 20, which will give us 140. Okay, so that's little tricky. Sometimes we might just write it as 160. But we need to know that 160 is from the vertical axis, which is this. We started from, this is our initial position. We started from this as our initial position. So from initial position, how much more we have to rotate? That will be 140. Okay. Okay, so let's check the next problem, which is on electricity. So it says here, the ends of a metal resistance wire are connected to the battery of electromotive force 8 volt and negligible internal resistance. The power dissipated by the resistance wire is 36 watt. What is the current in the resistance wire? So we have got the voltage 8 volt. We have got the power 36 watts. It's asking for current. We know that P equal to V times I, which can be rearranged as P over V. So 36 over 8, that gives us 4.5. That's our answer. Next is asking number of free electrons that passes through the resistance wire in a time of 50 seconds. So number of free electrons comes in the formula for current, where charge can be replaced by N times E over T. So we can just substitute the numbers here. N is what we don't know. E is 1.6 times 10 to the power negative 19. That's a constant. T is given to us as 50. We can use our calculator to solve it for N. The answer will come out as 1.4 times 10 to the power 21. So that means we will arrange this equation. We can write it as N in case if you don't know. how to arrange. We'll take 50 on the other side. So that becomes 50 over 1.6 times 10 to the power negative 19, and we can solve it to get the final answer. Next, the resistance of the wire. Resistance is defined as voltage over current. So voltage is given to us 8, current we have calculated 4.5, which will come out as 1.77, and again we'll round it off to 2SF, it will become 1.8. Next, it is giving us the resistivity and the area of cross section. It is in millimeter square, so area of cross section will be 0.25 times 10 to the power of negative 6 meter square. This is in millimeter square. We have to convert that into meter square, and that has to be multiplied by 10 to the power negative 6. Okay, in case if you don't remember, millimeter to meter, we have to multiply by 10 to the power negative 3. Because it's millimeter square, so we will square this as well. So that will become 10 to the power negative 6. Then we'll use the formula for resistance, length, resistivity and area, which is R equal to rho L over A. Substitute. What's the rho given? 1.4 into 10 to the power negative 6. The length is not known. Area of cross section is 0.25 times 10 to the power negative 6. We can calculate this to get the value of L. It will come out as 0.32, and that's our answer. Okay, next, what it says, the circuit which is shown to us in the previous figure is modified by replacing the original resistance wire with a second resistance wire. The second resistance wire has a greater diameter than the original wire. There are no other differences between the between the second wire and the original wire. And what are they asking us? By reference to resistance, state and explain whether the power dissipated by the second wire is more than, less than or same as the power dissipated by the original wire. So what's the connection between power and diameter? We know that power has a formula P equal to V square over R. Now, why am I using this formula? Because voltage is same. We did not do anything to the battery, but definitely the resistance is changing because we are using greater diameter. So I need a formula where two of the quantities are changing and one of the quantities remains constant. So V square for us will remain constant here. Now what we can do is we can also replace this R with its formula rho L over A. We will just arrange it. So V square over A rho L. Now if you check, V square is constant, resistivity is constant, length is constant. The only thing which is changing is area. And what is happening to area? The greater diameter means the area is going to increase. Yeah, so power is directly proportional to area. If area increases, diameter is increasing, that means area is going to increase. So what's going to happen to the power? The power will also increase. And that's what we can write in sentence form. Okay, I'm leaving it there. We can write it as a sentence. Then circuit shown in figure 6.1 is modified by connecting a second battery, which we can see here. Now there are two batteries. By reference to the current in the resistance wire. So by reference to the current in the resistance wire, state and explain whether the addition of second battery causes the power to increase, decrease or stay the same. This time we are going to choose the formula V times I. Because, why are we choosing V times I? Because we know that the battery is connected in parallel. You can see that battery is connected in parallel. That means the voltage across the resistance wire will remain constant. And power is depending on voltage and current in this formula. We did not do anything to the resistance wire. both voltage and current, they both are constant. So as I and V remain constant, therefore P will also remain same. Okay, we also can write like we can say that as the battery is connected, as the second battery is connected in parallel, therefore the voltage across the resistance wire remains same. Okay, because the batteries are connected in parallel, so the voltage will remain same, and therefore the current will also remain same, and the power remains same. Okay, a nucleus of sodium-22 decays by beta plus particle, and beta plus is released when proton gets converted to neutron. So we'll have beta released, plus there will be a neutrino released. So state the name of another lepton, and that's neutrino. An electron neutrino is released. Determine the nucleon number and proton number. So sodium 1122 is decaying by beta release. Yeah. So what should be left? Here you have got 1, here 11, so 10. And on the top we should have 22, the same number. So let's just say some element X is released. We just want to check what is the nucleon number and proton number. So nucleon number is 22 and proton number is 10. The quark composition of the nucleon in sodium nucleus is changed during the decay. Describe the change to the quark composition of nucleon. So what's happening is proton is converting to neutron. So proton is converting to neutron. So let's check what's the quark composition. Proton was, what is proton? Up, up, down, and neutron is up, down, down. So what's happening here is one up is getting converted to down. So the change, what's happening to the quark composition? One up, one of the up quark is getting converted is converted to down quark. Okay. A baryon consists of quarks that are of same flavor type. The charge on baryon is -2e, where E is the elementary charge. You want to find the charge on each quark. There will be 3 quarks. Total charge is -2. So for each quark, you have to divide by 3. So that will be -2/3e. Okay, -2/3e. Now, look at the charge and we can answer the next one. What is the possible flavor type of the quark? So 2/3e is for up quark, 2/3e is for the up quark. But this is negative, so we can write it as anti-up. Okay, so that's how we can complete this paper. That's the end of this video.